everyone, my name is Jeremy 136180026. We are going to talk about space debris and the technologies to mitigate them. First off, the reason we chose this topic is that ever since the first man-made satellite, the Sputnik 1 in 1957, there is a constant growth in space debris due to increasing amount of space travel and satellites. And with the prediction that the amount of satellites is going to quintuple over the next decade, we simply want to know whether it is possible to mitigate the increase in space debris. So, what is space debris? Space debris is defined as a collection of defunct objects which orbit the Earth, either natural or artificial. Natural space debris includes asteroids, comets, and meteorites. Artificial space debris, or often called as orbital debris, is defined by NASA as any man-made object in orbit above the Earth which no longer serves a useful function. Such debris includes non-functional spacecraft, abandoned launch vehicle stages, mission-related debris, and fragmentation debris. As of February 2020, according to European Space Agency, there are over 34,000 debris that has the dimension over 10 centimeters, and there are over 900,000 debris that has the dimension of 1 to 10 centimeters, and over 128 million debris that has the dimension less than 1 centimeters, which all accumulated to over 8,800 metric tons, which increases every year. In 1978, NASA scientist Donald J. Kessler proposed a scenario in which the density of space debris in lower Earth orbit is high enough that one single collision may trigger chain reaction that could end up making space activities impossible for generations. It is popularized as the Kessler syndrome, which is portrayed in the movie Gravity.
And then let's talk about the source of debris. The first one is dead spacecraft. On February 2015, the USAF Defense Meteorological Satellite Program Flight 13 exploded on orbit, this creating at least 149 debris objects, which were expected to remain in the orbit for decades. And then the lost equipment. The first one is a glove lost by astronaut Ed White on the first American spacewalk, or EVA, and then a camera lost by Michael Collins near Gemini 10, and then a thermal blanket lost during STS-88. The third one is booster. On 11 March 2000, a Chinese Long March for SBERS-1 upper stage is exploded in the orbit, so it's creating a debris cloud. And then on 19 February 2007, a Russian Bridge M booster stage exploded in orbit or over South Australian weapon. And then in 1980s, with the fourth ISM 135 AS80, this is a 1985 test destroyed a 1-ton satellite orbiting at 525 kilometers. This is creating thousands of debris larger than 1 centimeter. And then the source of debris came from collision. And then let's talk about the space debris mitigation. There are many ways to overcome space debris by several means. The first one is short-term means. And the point of this is prevention of in-orbit explosion. This is via passivation of space object at the end of their operational life. And the second one is collision. This is via collision avoidance maneuvers while the objects are still active.
Another way to mitigate space debris is through long-term means. This is shown by strong compliance with post-mission disposal guidelines to stabilize the space debris environment at a safe level. Under the United Nations, there is a committee known as United Nations Committee on the Peaceful Uses of Outer Space. The mitigation guidelines made by the committee are given. And then there's the end-of-life disposal. Satellites and orbital stages to be commanded to re-enter Earth's atmosphere within 25 years of mission completion if their deployment orbit altitude is below 2,000 kilometers, which is in the low Earth orbit region. The only viable option for satellites and orbital stages in or near the geostationary ring is to reorbit after mission completion to a graveyard orbit. The recommended reorbit altitude is about 300 kilometers above the geostationary orbit ring. This is due to the fact that low Earth orbit and geostationary orbit regions are denoted as protected regions owing to their commercial and scientific value. Satellites going to Lagrange points should also perform an end-of-life maneuver to clear the region for other spacecraft and to ensure that the satellite will not come back to Earth in an uncontrolled way. End-of-life disposal can be classified into two, which are passivation and design for demise. Passivation means that all latent energy reservoirs of a satellite or orbital stage are depleted to prevent an accidental post-mission explosion. Passivation can be done through four methods, which are depletion burns, fuel or pressure venting, discharging of batteries, and inhibiting of pyro devices.
Alright, so another part of end-of-life disposal is called or known as design for demise. And for what we should comply with this design for demise, that meeting on ground safety requirements in case of an uncontrolled re-entry must be considered during the design of space systems. And the engineering process that is established for intentional design, assembly, integration, and testing of spacecraft, it must be made in a way such that the space system will fragment in a desired way during re-entry and not cause a threat to people or property on Earth. And then the next type of disposal is known as the re-entry disposal. What happens in this process is actually hardware will burn up while re-entering the Earth, but the downside is that it is not completely burned up into dust. It's only like chunks or lumps, and then this disposal process must be done so carefully, so thoughtfully, because this may pose hazard to people and property on the ground on Earth, because that's chunks, so that when it is hit or become in contact with something or someone on Earth, and it goes with very high velocity, of course that the kinetic energy will be very, very big and therefore harmful. And the examples for this re-entry disposal are Cosmos 954, Skylab, Russian Mars 96, Delta 25, disposal of Mir Space Station, and Shuttle Columbia. Alright, so we all already know this technological ideas for mitigating the space debris. And then what is the implementations in actuality? Well, there are some implementations, the current implementations for space debris mitigation as for now. The first one is called the Clear Space One. This project is founded by Swiss startup company Clear Space. And what is the actual purpose for this Clear Space One? It is to find and remove the non-functional satellites that are still orbiting the Earth. So we need to remove all this. And then how it works? Well, it uses sensors to determine the location of a payload adapter called VESPA. This is actually the remains of a previous rocket launched in 2013, codenamed Vega. And then it will launch a chaser to attach to the VESPA. Once the chaser is attached via 4 robotic arms, a controlled re-entry will go into the Earth's atmosphere. And then, what is actually the goal of this re-entry? It is to burn up not only the target, but also, in this case, the Vespa and the chaser.
Another new project which seeks to mitigate the dangers of space debris is the Vestigo Aerospace program. The purpose of the program is by greatly increasing the frontal area of the debris, you can increase the object's aerodynamic drag. This will accelerate the object's orbital decay, thus incinerating the debris. It works by using drag sails on both functioning and non-functioning satellites, as well as launch vehicle stages. The decommissioned satellites will eventually be burnt out, incinerated in the denser layers of Earth's atmosphere. This also means that the drag sails remove the need for propulsion-based re-entry systems. Currently, Vestigo Aerospace is working on a 6-month study regarding the use of drag sails. Last but not least, we have the Remove Debris program. The Remove Debris program is a joint project, a consortium effort, led by Airbus and co-funded by France, Germany, UK, and South Africa. The Remove Debris program introduces a harpoon of sorts as an accessory attached to the International Space Station in order to pierce a piece of space debris and return it to the spacecraft. The harpoon itself is about the size of a pen and is made of titanium. A ground control team in United Kingdom sent both the harpoon and the spacecraft a series of commands, which were run autonomously by the spacecraft itself. Once the harpoon, launched at 20 meters per second, pierces the debris, a spring-loaded mechanism within the harpoon deploys an array of barbs to secure the harpoon firmly in place. In short, there are many forms of concepts and solutions to mitigate the space debris issues, both short and long-term means. Additionally, the method of re-entry and end of disposal, which consists of passivation and design for demise, can be applied as well. New mitigation policies have been developed and refined further to combat the dangers of debris floating about in space, along with new technologies or projects to predict collision, re-entry, and other related hazards. However, to minimize the dangers of space debris to the future generations, governments, manufacturers, operators must recognize the dangers and find or invent new technologies, not just to reduce the current amount of space debris, but also to create new and safer satellite technologies which won't become another space debris problem for the future generations. Through this presentation, we hope that people will become well aware of the dangers space debris may pose to mankind. Thus, further technological advancements may someday overcome this issue. Thank you for listening to our presentation.